In this fast-paced 40-minute lesson, we'll jumpstart your skills in writing Arduino programs using the new Arduino Uno R4 WiFi. We will cover things like data types, variables, constants, and control flow with conditions and loops, such as if-else, switch case, while, do-while, and for loop structures. We'll build custom functions to support modularity and reusability. Finally, we'll write scalable and efficient codes using arrays for organized data collection and storage. We'll put these concepts into action by controlling LEDs and reading switches to perform various LED sequences. Whether you're a beginner or an experienced programmer in other languages, these learnings will help you write comprehensive Arduino codes and build amazing IoT projects. Hey everyone, it's me, Joe Edgo, and welcome back to Education is Life. Today we're on Lesson 2 of the series, Level Up with Arduino Uno R4 WiFi, IoT Development Crash Course. Throughout this series, we will be working alongside this 52Pi Cloud-Ready Starter Kit. If you're interested, you can check it out on their website at 52pi.com or at Amazon. Links are provided below. Again, thank you so much 52Pi for sponsoring this crash course. Now, before we dive in, make sure that you have downloaded your Arduino IDE and configured the Arduino Uno R4 boards. If you haven't, please watch the previous lesson. To start, let's talk about the basic structure of an Arduino program. An Arduino program consists of two mandatory functions, the setup and the loop functions, and an optional section for variable declaration and preprocessor directives. This section placed at the beginning of your code allows you to define global variables to store data that can be used by all functions during program execution. It also allows you to include references to external libraries that your program might need, like graphics, networks, sensors, and many more. By the way, this is a comment, denoted by these double / symbols. And anything you put in your program with these symbols gets ignored during program execution, like this one and this one. This setup function runs only once when you first power up or reset your Arduino board. It's like the initialization phase where you set up things like defining whether a pin will be used for input or output, or initializing a sensor object to begin sensor readings. Now, the loop function is the heart of your program and runs continuously in a loop, repeating its instruction over and over again. This is where you place the code that controls your Arduino, like reading an actual sensor data or controlling output LEDs or other devices connected to your Arduino Uno, like motors, speakers, or displays. This is the place where you typically perform programming calculations. Here, we use standard programming logic and operators to manipulate data and make decisions within the loop. Let's first implement this circuit diagram to start writing Arduino programs. If this is your first time implementing a circuit connection on a breadboard and you want to have a deeper understanding of how these components work in detail, I highly recommend watching my other lessons on the Arduino Uno R4 Minima series. Links are provided below. Now, to implement this circuit, we need the following materials: 4 pieces LEDs, 4 pieces 1 kilo ohm resistors, 2 pieces normally open push-button switches, a breadboard, some connecting wires, and your Arduino Uno R4 WiFi. Here, we have 4 LEDs, each with a 1 kilo ohm current limiting resistor connected to pins 10, 11, 12, and 13 respectively. Please note that the anode or the positive terminal of the LED is the one connected to the resistor and to the pin, and all their cathode terminals are commonly connected to the ground of the Arduino board. A quick note also for those previously working on Arduino Uno R3, the new Arduino Uno R4 WiFi has a maximum current draw of only 8 mA per GPIO pin. This is significantly lower than the previous versions. The older Uno R3 has a maximum current rating of 40 mA or 20 mA continuous current. And for that, we need to use a bigger resistor value of about 1 kilo ohm so we don't draw too much current that could exceed the maximum current rating. For a detailed discussion of how we got this resistor value, please see the links below. Finally, we have 2 push-button switches connected to pins 2 and 3. Please also note that we didn't use any pull-up or pull-down resistors here because we will configure these pins later to use the Arduino's internal pull-up resistors. Now, let's talk about the building blocks of any program, data and variables. Variables act as little containers inside your Arduino that hold the data your program needs to work with. Data comes in different types like numbers, text, and true or false logic values. Arduino offers a range of variable types, each suited for storing different kinds of data. Here are some of the common ones. Int to store whole numbers, positive, negative, or 0. So for example, to declare a variable of type int, we can type int and then follow by a variable name. Variable names could be any valid identifier consisting of upper and lowercase letters, underscores, and digits. For example, LED1 underscore pin or short underscore delay. Then, we use an equal assignment operator to assign a value followed by a semicolon. We use a semicolon to end a statement in Arduino code or what we call the sketch. It is like a period to mark the end of a sentence. Now, since this new Arduino Uno R4 WiFi uses a 32-bit microprocessor, an int data type stores a 32-bit value or 4 bytes. This means that we can store whole numbers from -2 billion up to +2 billion. On the other hand, if you want to store numbers with a decimal point, use the float data type instead. Floating point numbers are often used to approximate analog and continuous values because they have greater resolution than integers. For example, we can use this type to store a temperature reading or a voltage reading. Now, the car data type allows you to store a single character value. We use single quotes like this to denote a character literal. Please note that characters are stored as numbers. You can see the specific encoding in the ASCII chart. This means that it is possible to do arithmetic operations on characters. So this variable declaration, car choice equals 65, is the same as the above. The Boolean type makes things simple, storing only true or false values, perfect for making decisions in your code, and we'll explore this further later. So just a quick note, not all variables that you're going to create are equal in terms of accessibility. Some of them will be declared within a specific function and can only be accessed within that function. These are called local variables. Now, let's put these variables and data into action. Let's control these 4 LEDs by turning them on one by one. For that, let's create 4 variables of type int that will hold the pin numbers assigned to these 4 LEDs. Let's call them pin LED1, pin LED2, pin LED3, and pin LED4, and then assign pins 10, 11, 12, and 13 respectively. Now, in the setup function, we need to initialize everything. In Arduino, there is a built-in function called pin mode, and we need to use this to set the mode of these pins as either input or output. Since these pins are all connected to LEDs, we configure them as output. In the loop function is where the actual code that triggers these pins to go high one by one, starting from pin 10 up to pin 13, so that each LED attached to these pins will light up one by one. To change the state of the Arduino output pins to either high or low, we call another built-in function digital write. To use this, we specify the pin as the first parameter and then a high or low constant. In Arduino Uno R4, high means to set logic 1 or 5 volts at the specified pin. Low, however, means logic 0 or 0 volts. Please note that Arduino is case sensitive, so make sure to observe the proper casing when you type variables, constants, and function names. Now, since our goal is to turn on all the LEDs one by one, starting from pin 10, let's first call digital write to turn on the LED 1 at pin 10. Then, let's have a short pause before turning on LED 2 at pin 11. To do that, we can call the delay function here, where we can specify a time delay in terms of milliseconds. Here, instead of putting a numeric literal, we'll use the delay variable we declared earlier. This short delay, which means that our code will pause for half a second before executing the succeeding line of code. Now, let's just copy this and replace the pin to turn on. So to complete the sequence, we simply copy these 2 lines of code twice and replace the pins that correspond to LED 3 and LED 4. At this point, all LEDs are turned on. And once our code reaches this closing curly bracket of this loop function, it loops back and repeats the code execution again from top to bottom. Now, one last thing before our code loops back, we need to turn off all the LEDs so that we can see them again turning on one by one. Here we call another delay and set all the LED pins to low. So let's see if our program works. And it works as expected. When declaring variables, we sometimes use a variable qualifier called const that modifies the behavior of a variable, making it read-only or constant. This means that a variable can be used just as any other variable of its type, but its value cannot be changed. So in this sample program, if we don't want to accidentally change the value of the pin assignment to LED 1, LED 2, LED 3, and LED 4 along the course of program execution, putting the keyword const will make sure that these variables' assigned value will not change. And when we upload the code, you won't see any difference as it performs exactly the same. Arduino code is generally executed sequentially, one statement after the other. So the order in which your statements are placed matters. Now, Arduino offers several control structures that allow you to adjust the flow of your program. First, let's talk about the conditional if statement. The if statement is the most basic of all programming control structures. It allows you to make something happen or not, depending on whether a given condition is true or false. To demonstrate this concept, let's modify this program to include a button connected to pin 2. And this is our new desired output. When the button is pressed, the LEDs turn on one by one. Otherwise, all LEDs turn off. To accomplish this, let's declare another const variable of type int to hold pin 2. In the setup function, we use the pin mode function to set pin 2 as input pull up instead of output. We can also use input constant instead of input pull up if we have explicitly implemented either a pull up or a pull down resistor in our circuit connection, because this physically puts our button in a known state of either high or low when the button is not pressed. However, in our circuit connection, this button pin is in a floating state. This means we cannot say for sure if it is high or low, and it could vary depending on a lot of factors. Now, the good thing is that Arduino Uno offers an internal pull-up resistor that we can enable by simply setting the pin's mode to input pull-up, so we don't have to add our own pull-up resistor externally. With this, our button pin's default state is high when it is not pressed because it is internally pulled up. And the moment we press this button, the input pin goes low. Before we create an if condition, let's first create a local variable of type int that will store a 1 or 0 value, which basically represents high or low respectively. Or we can use a Boolean type that stores only two values of either true or false to represent 1 or 0 as well. Now for this to work, we'll call the digital read function to read the state of button 1. In return, this function gets the pin's state, either high or low, and stores it to this button 1 state variable. Now, using an if statement, we can simply check if button 1 state is equal to low, meaning the button is pressed. Then we enclose everything inside this if block, meaning this code that performs the sequence of turning on 4 LEDs one by one will be executed only if button 1 is pressed. Let's upload the code and see if it works. So now, our code is continuously reading the state of button 1 and then checks if it is pressed. Since we're not pressing it now, the button state remains high, and this condition is evaluated as false. Thus, it skips the entire code block. But the moment we push the button, putting pin 2 into a low state, the condition is evaluated as true and the code is executed. In this program, you'll notice that it only executes the code block when the condition is satisfied. But if the condition turns out to be false, it doesn't do anything. When using an if statement, there is an optional code block that we can use if we want to perform an alternative course of action when the condition is not satisfied. Say we want to make all LEDs blink when button 1 is not pressed, instead of simply turning them off. To do that, we put the else keyword and write a blinking code inside this block. I'll just copy this set of code twice, and then change these first 4 lines to high so that all LEDs turn on, followed by a short delay, then turn off, and then a short delay again. And then loops back to check again whether button 1 is pressed or not. Let's upload the code and see if it works. And as you can see, we have a blinking light by default since button 1 is not pressed. Here, the else block gets executed. But the moment we push button 1, putting button pin 2 into a low state, the condition is evaluated as true and the code inside the if block gets executed. Again, when I release the button from being pushed, the control of the program gets redirected to the else block to perform the blinking sequence. In an if-else statement, the control flow is either to perform the if block or the else block. When the condition is true, then perform the if block. Otherwise, perform the else block. But what happens if we want to check for multiple options of conditions so that we can perform a corresponding action depending on which condition is satisfied? In that case, we can use an optional else if block. Else if must be placed after the if block. If there's an else statement, it must be placed before the else block. Now, if the above condition is evaluated as false, the control goes to the succeeding else if block to check for another condition. We can add as many else if blocks as we want. The important thing to understand here is that only one of these blocks get executed. It means that even if all conditions were to be evaluated as true, it would never reach that point when using an else if condition. That is why it is called else if, because it only checks for another condition if the preceding condition fails. But when the preceding if or else if condition is already satisfied, then the rest of the succeeding else if blocks will be ignored. Here, the order of conditions matters. The first if or else if condition to be satisfied is the only one to be executed. Now, to put this into action, let's include another button connected to pin 3. Let's call it pin button 2. Of course, we need to set the mode to input pull-up. Finally, we create another Boolean variable button to state and read the pin state at button 2. Since we already have 2 buttons, we can now make 4 possible combinations out of this. First, none of the buttons are pressed. Second, button 1 is pressed but not button 2. Third, button 2 is pressed but not button 1. And fourth, both buttons are pressed. So now, here is our new program requirement. When none of the buttons are pressed, then make the LEDs blink. When button 1 is pressed but not button 2, then perform the sequence of turning on all the LEDs one by one. When button 2 is pressed but not button 1, then make the LEDs blink alternately. Finally, when both buttons are pressed, we turn off all the LEDs. So, how do we do it? First, we need to re-examine what makes up a condition inside an if statement. Conditions may contain relational and or logical operators. Relational operators compare values to determine a relationship and return a Boolean result of either true or false. For example, we can use greater than, less than, greater than or equal, less than or equal, is equal, or not equal symbols. Then, on top of this, we can include logical operators to combine true or false values to create more complex conditions containing logical and, or, and not. So for example, in our first condition, what we want is to check if none of the buttons are pressed. To translate that into a conditional statement, we can ask if button 1 state is equal to high and at the same time, button 2 state is equal to high. Here, we use the logical operator AND, denoted by this double ampersand symbol, to produce a final condition that will only yield true if both conditions are true. That is, both buttons are not pressed. However, if at least one of the 2 conditions is not satisfied, which means if at least one of the 2 buttons is pressed, then the entire condition will be evaluated as false. And then, inside the if block, we can perform the blinking program. So, I'll just cut and paste this blinking code here. Then, for our second condition, I'll convert this to else if and check if button 1 state is equal to low and at the same time button 2 state is equal to high. Again, we use the logical operator AND to make restrictions that this condition will only be evaluated as true if button 1 is pressed but not button 2. We didn't use logical OR here because if we do, then only one of these 2 conditions needs to be satisfied for this entire condition to be evaluated as true. we will lose those restrictions. In effect, all four possible scenarios will fall under this condition, which is not really what we want. Think about that for a moment. So, we retain the codes inside this block, since this is the code that performs the sequence of turning on all the LEDs one by one. Then, for our third condition, we simply reverse the previous condition, checking if button 1 state is equal to high and button 2 state is equal to low. If this condition is true, then perform the following. What we want here is the alternating blinking LED. So, let's simply copy these codes and paste them here. Then change LED 2 and LED 4 to low. And after that, change LED 2 and LED 4 to high. Finally, our fourth condition is to check whether both buttons are pressed, and if so, we turn off all the LEDs. Here we can explicitly put another else-if block to specify this condition, or we can simply use the else block without having to specify any conditions at all, because this is the last and the only possible scenario or combination left that we have not checked yet. We are sure that if none of the first three conditions are satisfied, then for sure, button 1 and button 2 are pressed. So I'll remove this last else-if block and use this else block instead. Inside this, I'll just copy the code that turns off all the LEDs. And that's it. So let's see if it works. As you can see by default, when none of the buttons are pressed, the LEDs blink. To test the second condition, I'll press button 1. And it performs the sequence of turning on all LEDs one by one. Now, the moment I release button 1 from being pushed, the operation goes back to the blinking LEDs again. Now, I'll press button 2 to test condition 3. And it performs the alternating light sequence. Finally, when we press both buttons, all the LEDs turn off. There is another control structure quite similar to if and else if statement. This is called switch case. A switch statement compares the value of a variable to the values specified in the case statements. When a case statement is found whose value matches that of the variable, the code in that case statement is performed. Here, the variable being tested could be any integer-related type whose value is to compare with various cases. It can work with byte, char, int, long, and bool data types. Now, the break keyword exits the switch statement, and it is typically used at the end of each case. Without a break statement, the switch statement will continue executing the following expressions until a break is encountered, or the end of switch statement is reached. The default keyword is similar to an else block. If nothing else matches, perform the default code. To apply in our sketch, let's declare a variable to be tested. Let's call this counter and set its initial value to 0. Now, here is our new program requirement. Instead of using 2 buttons to perform all these sequences of LED lights, we'll use only one, button 1. The first time we press it, it should perform the blinking LED sequence. The second time we press it, it should perform the sequence of turning on all LEDs one by one. The third time we press, it should perform the alternating light sequence. And the fourth time we press, it should turn off all the LEDs and the cycle repeats. To accomplish this, let's check first if button 1 is pressed. If so, we'll increase the value of the counter variable by 1. We can do this with a simple arithmetic operation like counter is equal to counter plus 1, or we can simply apply this plus plus unary operator to increment the value of the counter variable by 1. Now, let's put a short delay here, about 1/4 of a second, so that it debounces a little bit to stabilize the bouncing effect of the internal mechanism of this button. This is to confirm that we indeed press this button only once before proceeding. We don't want our counter variable incrementing several times with just a single push. A quick note, this is not the proper way to debounce a button since we didn't check if button state changes. This approach is a temporary remedy for this current topic using a delay function, and the use of millis function will be discussed in future lessons. Now, before we implement the switch statement, let's accomplish this using the if statement. Let's check if the counter variable is equal to 1, then perform this blinking LED sequence. Else if the counter is equal to 2, then perform the sequence of turning on all the LEDs one by one. Else if the counter is equal to 3, then perform the alternating light sequence. Finally, if the counter variable is not equal to 1, 2, or 3, then reset it to 0 and turn off all the LEDs. Let's upload the code and test our prototype. As you can see by default, since the counter variable is initially set to 0, the control goes to the else part, thereby turning off all the LEDs. Now, the first time we press button 1, the LED blinks. The second time we press it, the second sequence gets executed. The third time we press it, the LED blinks alternately. And the fourth time we press it, all LEDs turn off and the cycle repeats. Now, let's convert this if structure into a switch case control structure. We need to put this counter variable to be tested for equality. And then I'll move this entire code inside the switch block. Then replace each if condition with a case keyword. This pair of curly braces are no longer required here. Finally, make sure to put a break at the end of each case. We'll do the same for the rest of the else if blocks. And now, let's upload the code and verify if it works. And it works exactly the same. Now, before we discuss looping and arrays, you'll notice that our code starts to clutter a bit. We also have several lines that we are just repeating in different places. One way to organize our code is to segment it into functions. This will allow us to create modular pieces of code that can perform defined tasks and can be called several times. This promotes code reusability. We know that there are two required functions in Arduino Sketch, the setup and the loop functions. But in addition, we can create custom functions that we have to define outside the brackets of these two functions. For example, we can create a function to turn off all the LEDs. We'll call it LED off. A function definition is denoted by this pair of parentheses. And then, let's move this code that turns off all the LEDs. Now, since we have this function, we can simply call its name in any part of our code that requires turning off the LEDs. We can call this function here as well, and in here. In effect, it simplifies our code. Let's create another function and give it a name, LED on. Then move this code inside this function. Finally, let's simply call it from here. We can create as many functions as we want to make our code more manageable. For example, we can put this sequence into another function and we'll call it incrementing LED. Same with this case tree, let's move this code into another function we'll call alternating LED and call it here. As you notice, our main loop is now more organized and readable. Make sure to upload your code and test if everything works the same. And it works as it is. Arduino offers three common looping structures: the while, for, and the do-while loop. Looping statements allow us to repeat portion of our codes. But unlike this mandatory loop function that continuously repeats again and again, looping statements can be performed and terminated based on certain conditions we set, similar to an if statement. Basically, any of these three looping statements can be used to achieve a similar programming task. However, for specific situations, one loop type might be more readable and easily achieved than others. Consider this incrementing LED function. We can rewrite this to use any of the looping statements for scalability and code efficiency. We can see patterns in this code that are repeated with only minor differences. In fact, at closer inspection, these lines look identical except for these pins that were turning on after every loop. Now, we know that LED 1 is at pin 10, LED 2 is at pin 11, LED 3 is at pin 12, and LED 4 is at pin 13. We can modify this to use only one variable instead of 4, and then increment that variable by 1 after every loop, so we can remove the rest of these duplicated codes. First, let's declare a local variable pin LED and set it to 10. This is the starting pin for LED 1. Then, we'll use the while loop construct. Inside this while condition, we check if the pin LED variable is less than or equal to 13, which is the last LED pin, and then we allow the code inside to happen. Inside our code, we'll use this variable so that we send a logic high signal to the pin pointed by this variable. After the code execution, it loops back to check the same condition. Once evaluated as true, the code inside is performed again and again until this condition turns false. But when it is going to happen? According to our condition, when the last value of the pin LED is no longer less than or equal to 13. That's 14 and above. So, inside this while loop, we make sure that this thing happens so that we avoid going through an infinite loop when the condition is always true. Also, that's the main reason why we replace this with just a single variable instead of having 4 individual variables that point to different pins. We can simply increment this pin LED variable so that the next time it loops back, it points to the next LED pin until it reaches the 4th LED, and then the loop stops. If this function is again called, the pin LED variable is reinitialized to 10 and the LED sequence is performed. Let's upload this code and see if it works. And it performs exactly the same. This while loop can be easily converted into a do-while loop. All we have to do is to move this while condition at the end of the code block and put a semicolon to denote the end of the statement. Then, replace this starting statement with a do keyword, as in do it first without asking, then ask later if it is allowed to loop back. And this condition allows our code to loop back while the value of the pin LED variable is still less than or equal to 13. This code should produce exactly the same result as before. Let's try it. And it works exactly the same. In some situations, you'll see a different result because the do-while loop executes the loop body at least once. Remember that the while loop evaluates the condition first and then executes the statement when the condition is true, whereas the do-while loop first executes the statements and then evaluates the condition after if it can loop back. There are many portions of our code where we can apply looping statements. For example, in the setup function, when we set the pin modes of these 4 pins to output, we can simply remove these repeated codes and create a loop to do that. Now, instead of using the while or do while, let's try implementing it using the for loop. The for loop structure is more compact as it includes everything on a single line. The variable initialization followed by a condition and an increment expression. Here, we initialize the pin LED variable to 10. Then, checks if it is less than or equal to 13. If so, the statements inside the loop get executed. Then, it loops back to increment the pin LED variable by 1 and ask the same condition if it is still true or not. If true, perform the code inside and loop back to increment. Once the condition turns false, then the loop is terminated. Let's upload the code to verify whether the output is the same. And it works exactly the same. In addition to many good use cases of looping statements, they work best in conjunction with arrays. As you notice in our code, we typically change the content of a variable inside the loop so that each iteration performs a little differently than the previous one. Like in this case, the value of the pinlet variable changes from 10 to 13 in sequence so that we can set each pin's mode to output. Now let's change the situation a bit. What if these 4 LEDs are no longer connected in sequence to pins 10, 11, 12, and 13? Let's modify this circuit connection and place LED 1 to pin 7, LED 2 to pin 8, LED 3 to pin 11, and LED 4 to pin 13. Now, just by incrementing the LED pin variable is not going to work this time. There's no obvious pattern of how to alter this variable's content to follow the sequence 7, 8, 11, 13. With that, let's introduce the concept of an array. An array is a consecutive group of memory locations that holds multiple data of the same type. For example, instead of having 4 different variables to store 4 different pin numbers associated with each LED, we can declare one array variable that contains 4 data inside it. Declaring an array is almost similar to an ordinary variable except for this pair of square brackets. Inside, we place how many items this array is going to hold. In this case, 4. Upon declaration, we can already initialize the array content by assigning the values enclosed in a pair of curly braces, separating each value by a comma. Here, we put the pin numbers 7, 8, 11, and 13. These values will be arranged in sequence in memory once the program runs, and we can access these individual items through an index. Arrays are zero-based index, which means the first item is given an index of 0, the second item is index 1, the third item is index 2, and the fourth item is index 3. To access an item of one array, we write the array name and put the index number in square brackets. For example, LED pins index 0 will access the first array item, which is 7. LED pins index 1 will access the second array item, which is 8. LED pins index 2 will access the third array item, which is 11. And LED pins index 3 will access the fourth array item, which is 13. Now, we see a similar pattern to how we can access these pin numbers in sequence through array index numbers. Here, we can use a variable that counts from 0 to 3. Let's call it index. With that, we initialize it to 0, check if index variable is still less than 4, that's 0 to 3, and increment it by 1 after every loop. And that's it. This pin mode function will be called 4 times when the index variable is 0, 1, 2, and 3. Thus, pins 7, 8, 11, and 13 are initialized one by one as output. Now, since we modified the pin assignment in our circuit connection, we need to modify the rest of our code here as well, otherwise it won't work. For that, let's change these implementations to looping and arrays. To turn off all the LEDs, we can use a similar for loop statement. Let's initialize this I variable to 0. Let's use I instead of index for simplicity. Then I less than 4, then I++. Now, we only need one of these since the loop will be the one to execute this 4 times. Make sure not to forget to access the LED pins array and access its individual indexes with this variable I. I'll copy this code because it performs similarly to the LED on function, except for this logic high. In this incrementing LED function, let's apply a similar logic using this for loop. I'll just copy this and simply add this short delay before looping back to turn on the next LED in sequence. And I can get rid of this previous do-while code block. While we can achieve this code using a while or do-while loop, the for loop structure is generally easier to read and understand. Now, this last function is a bit tricky to implement a loop that uses an array. We can implement a similar for loop code, but this alternating high-low value makes it a bit harder to accomplish. We can see 2 possible looping statements here. The first high, low, then followed by a short delay, and the second high, low sequence, then followed by another delay. So here's what we're going to do. Let's copy and paste this same code twice, and after each loop, let's put this delay. Now, the main challenge is how to make this alternating high-low logic after every loop. Well, there's a lot of ways to do that, but here we're going to declare a Boolean variable. We'll call it LED state and initialize it to true. This is basically 1 or high. Now, let's use this variable inside this digital write function instead of this constant high. Now, this is supposed to go high, low, or true, false after every loop. This is where the unary logical NOT operator becomes useful. It's like this. If the LED state is previously true, we invert it to false. This is denoted by this exclamation symbol. So, the next pin value will be false or low. And if this LED state is previously false, this operator inverts it to true. So the next pin will be set to true or high. Now, I'll use the same approach to this other for loop. However, it should be in this sequence low, high. The simplest is to invert this LED state one more time before going through this second loop so that it starts low instead of high. Or, if we want to follow the same pattern of high, low, we could start from the last index down to the first index. That's index 3 to 0. All we have to do is to modify this starting index to 3. Then the condition is so long as this I variable is still greater than or equal to 0, then we decrement the I variable by 1 instead of incrementing it. And that's it. Now let's clean up our code and remove the previous implementations that no longer work. I'll get rid of these variables as well since we already use an array. Now, let's run our code and see if it works. And as expected, it works exactly the same. An array is a very powerful data structure that you can leverage when writing Arduino programs. It can improve your code significantly. What you've learned today is called one-dimensional array. For our next lesson, we'll take it to the next level by using two-dimensional arrays to write animations on your Arduino board's LED matrix. Again, thank you so much for joining me in the second lesson of this series, Level Up with Arduino Uno R4 WiFi IoT Development Crash Course. If you enjoyed this video, be sure to give it a thumbs up. And if you want to see more Arduino tutorials, please hit that subscribe button and ring that notification bell so you never miss a new upload. You can also share this video with your friends who might be interested in learning more about Arduino. The more viewers we have, the more in-depth content I can create for you in the future. So, keep learning, keep experimenting, and always remember, education is life. See you in our next lesson. Happy coding!